Yeah. Now let's share our screen like this. There you go. Let's admit more people in. Good. Okay. So I have the quiz here. Number 1. Determine with short justification if the following statement is true or false. So for all x, there exists a y such that y squared equals to x. Ugh. So there are two questions here. The first one is when the domain is the set of real numbers. I would say that the vast majority of you got that one right, which means 1, you can read the first order formula correctly, and 2, you know your real numbers. So
I don't
of
hear you. I
course,
don't know if anyone else does.
sorry.
No, we hear you. You know what's happening.
Yeah, everybody's okay. Can you hear me?
Yeah.
Is there anybody out there? Yes. So what was I saying? Set of real numbers. Then of course this is false. It is not true that every real number has a square root. Just take x equals to -1, for instance, right? And then the second one. Now I knew you could read the first order sentence, but then you messed up in the math. Many of you. So it's tempting to say, "Oh yeah, now it's okay because now we have only positives," but actually it's still false, but for a different reason, more subtle reason. Why is that? Is it true that every rational number has a square root, which is a rational number, right? So the domain, the world you live in when you're looking at this is only rational numbers. Well, no, because if you take x equals to 2, it's not true that there is a rational number squared that will give you 2 because root 2 is irrational, right? So some of you, many of you messed that one up. That's okay. That's where it's, I mean, now you know. Um, that's not a bad mistake. Okay. Number two was a car crash. It was too many deaths here. That was really bad. Um, so okay, let me try to explain what went wrong here. I know I'm no, I'm not going to try to explain what went wrong. I will point out what went wrong in various instances. So the first thing is if you don't know what that means, you can't answer the question, which was the case for some of you. Okay, so fix that, please. Okay. Second, and more importantly, is that first order formulas have a syntax that you have to follow. Think of it as a programming language. If you try to code and you don't use the proper syntax, the machine will slap you on the wrist. It will tell you, I have no idea what you're writing, please fix it. So this is exactly the same thing, okay? So here's how we can write this. So every positive integer, you see the every you're thinking for all, that's great, okay? Every positive integer is the sum of 4 perfect squares. So it means that you can write there exists a representation of your positive integer as the sum of 4 squares. So let's do that. So for every x, right? And the domain is integers, so that means for every integer, but that's not quite right. I need them to be positive. So I say if my integer is positive, then it can be written as the sum of 4 squares. In other words, I can find, or there exist, integers a, b, c, and d, it doesn't matter how you call them, such that x is the sum of these squares. So that's the simplest way to write this, okay? Um, let me do now number 3. I'll get back to 2 because okay, so I don't have enough room here to write everything I want to write about number 2, but I'll yes, please come in.
Sir,
Yep.
instead of putting them x is bigger than 0, can you say like for all x in P of x?
Oh yeah, sorry. I gave you're right. You're right. That's what I should have written actually. I mean the way I wrote it, yes. That's what I want. Yeah, I gave you a symbol to do. Yeah, but I certainly did not remove marks if you wrote x bigger than 0. I obviously that's not the big deal here. Okay. I'm giving you the predicates to actually try to make your life easier, because I want to make sure that you know exactly what you're supposed to use and nothing else. Okay. Um, okay. By the way, there's no need to write anything like this, and it's not supposed to be there. It is not given as a predicate anywhere, and it's not needed because the domain is all integer. So you don't need to specify that what you are. Wow, lots of chats. Sorry, I didn't see them. Oh, okay. Am I the only person who doesn't hear anything? Everybody says yes. That's always nice. Okay. Is everybody okay now? I saw, it seems to me that Joshua is with us now. And Mark fixed it. Good. Technology is wonderful. Yeah. Okay. Sorry, I didn't see the chats. Okay. Yep.
Also, sir,
Yep.
in your correction, for this number, you sort of like put two symbols. Is it either or is it like an arrow pointing here? There should have been something. There should have been that thing.
Did you have P of X?
Yeah, what I mean is there's the
Yeah,
and or symbols, but I don't know if you mean them as the symbols themselves or as the point of an arrow.
are you talking about what I wrote on your copy?
Yes.
Okay.
But I don't know if it's a case just for me or it's how you correct in general.
You'll have to show me because I don't really know what you're talking about. Sorry.
All right.
Okay.
I can do it after the class.
Yeah. All right. Good. Okay. Okay. So let me move to the proof, which was actually pretty good overall. Now, I discussed this with a few of you individually. Number 3, if you've never seen it before, that's sort of a moderately difficult problem. At this point in your mathematical life, this would be a pretty difficult problem. But this was the second assigned problem in the book. So I'm sort of assuming that you've seen it before. So that's different, right? So there's a huge difference between me assigning a problem that's in the list or not, right? So if you had seen it before, I think makes, I'm just repeating myself, I'm sorry. Okay, so let's do this. We want to prove that if m plus n and n plus p are even integers, then so is m plus p. There are 2 main strategies to solve this problem. There is a very long way and there is a very short way. Let me start with the short way. Okay, so m plus n is even. That means there exists some k, an integer, such that m plus n is 2k. N plus p is even. That means there exists some L integer such that n plus p is 2 times L. And now what I'm going to do is a bit of magic. I'm just going to add those 2 things together. So what I'm going to get is m plus n plus p is equal to 2k plus 2l. And what I'm interested in is m plus p. So I will solve for it. So I'm going to get this is equal to 2k plus 2l minus 2n, which is twice k plus l minus n. and hence it is even. That's the short proof. Okay. There is a longer way, which is correct, which is this. You argue that for m plus n to be even, either both m and n are even or they are both odd. Okay. The same is true for n plus p. They have the same parity, which means because n appears in both, that m and p must have same parity, and hence their sum is even. This is a correct argument. It is long, especially if you do everything correctly. So for those, some of you who tried this way, you just said, well, if m plus n is even, then m and n are even or they're both odd. But you have to prove that. You have to argue that they can't. Why is it the case that m plus n is not even if m is odd and n is even, for instance? So you have to write that down. You have to prove it. So that's painful and long, right? But if you do it, it's fine. I will not, I mean, if you write a 27-page proof for something and the proof is correct, then it's correct. That's math. That's the beauty of it. Okay, so I'm not giving or removing points for style here. I mean, correctness, but okay, let me go back to this number 2. Maybe I can just do it here. Let's use this. I don't know if this is going to work. Maybe it will. It didn't. Okay, as expected. Yeah. Okay. So bad things I saw. I'm not naming names. Okay. The first bad thing is incorrect syntax. Something like p of x and right next to it, x equals to a squared plus b squared plus c squared. Let's say something like that. I mean, this doesn't make, so, I mean, from a syntactical point of view, this makes no sense. P of x is a true or false, and it's right next to an equality. I mean, how are they connected, right? So connection, you have to connect, right? So there should be some or and implies something there, right? Okay, but the really bad thing I saw was, and I wish I hadn't seen that, but one scene, it's this. That hurts. That hurts bad. Okay, I'm not trying to make fun of anybody, but it just hurts. I'm sorry. So if you look on this, this is a number. This is an integer, right? That's the nature of this object. What is the nature of this? It is true or false. This is a truth value, right? So it's just exactly the same. Why are you, okay? It's exactly as writing something like true equals to 7. It's just like, no, okay? No, that's bad, okay? Don't do that, okay? That's bad, okay? So they have a different nature. They can't be equal, right? Okay. So be careful with the syntax. And let me do maybe a couple examples that I actually assigned. I don't know if you did them or not. I am aware that you have a lot of stuff to do, but on the other hand, I have to do my job too. So here is a couple of examples from the, this is from the document on Leia. And please, if you have questions or comments, just don't hesitate. So this is, okay, so we'd like to write if, why am I writing in red anyway? So if n is odd, then n squared is odd. So this statement, again, I said this should be universally quantified. It's understood that this means for any n which is odd, n squared is odd, right? So it's understood that we need a for all n. And that one is actually pretty straightforward if you know how to write down what it means for a number to be odd. So what does it mean for n to be odd? It means there exists a k such that n equals to 2k plus 1, right? So this is exactly saying that n is odd. And this should imply that n squared is odd. So there exists some L such that n squared equals to 2L plus 1, right? So that's how I would write this. So notice this is a proposition. This is a proposition. They are connected by implication, if then, and the whole thing is universally quantified for all n, okay? So like that. That's a first order formula, okay? So again, first order formulas involve only the given predicates, which are given. I will always specify what these are. Or, and, not, maybe implies, well, and you can use why not, some, and the two quantifiers. That's it. That's what a first order form correctly built. Now, I didn't give you a formal definition of a well-formed formula. I'm of two minds. I could write it up and it would be like, oh man, it's just so technical and just awful. On the other hand, if you had it, then it might help not going wrong. But I still think that at this point, because we're going to move on to something else like today. So after the test, first order formulas are just like, I've done what I had to do. And I don't want to go into that much more into that. So I'll keep it semi-informal, okay? Here's I want to do another one. No, I don't. I'll do more on Monday. If you have actual questions, I will be happy to do them on Monday. That would be nice. Okay, so questions, comments on this, on the quiz, or good? Okay, so I'm going to move on to chapter 4. I will start briefly. Let's start a new one. Okay. Chapter 4 is entitled, they call it number theory and cryptography.
Sir,
Yep.
for the number 3 in the quiz,
Yep.
we needed to like specify that the like M and like L and R were
Integers.
integers, yeah.
Yeah, to be
Okay.
super precise, yes, of course. Yeah.
Good.
Yeah, because I mean, in the context where everything is integers, if I just say there exists a L such that blah blah blah, then I don't really need to specify if it's clear that I'm working only with integers. But if then there's rationals or real numbers, then you have to be careful. But anyway.
Okay, good.
Yeah. Okay.
So
Yep.
is it safe to assume that we always have to define which part of, like, which group our numbers are part of?
I mean, if it's not clear from context, I mean, it's always better to actually, I mean, it's just, I'm being picky because you're starting. So I have to be sort of picky. But obviously if somebody says, oh, then there exists a number such that A equals to 2, there exists a B such that A equals to 2B and hence A is even. Obviously B has to be an integer. If it's not an integer, then, I mean, every real number is twice some other real number, right? So depending on context, I'll be picky or not picky, but
Okay, so it's safer to assume to just always specify which.
You're better to put more than not enough. Let's
All
put
right.
it that way. Yeah, I'm not going to be crazy going for all the little details, but at this level, I sort of have to some extent. Yeah,
All right. Thank you.
yeah. Okay, so chapter 4, number theory, cryptography. That looks like, I mean, that's huge. That's a huge title. But what we're going to do is this. Okay, so what we are going to do is this. Basically, is some basic number theory. By basic, I mean in terms of number theory is like the oldest branch of mathematics. I mean, it's like it's been done for thousands of years, and it's like now hyper deep, insane, crazy, right? So and it's wide. There's all sorts of different kinds of approaches to number theory, analytic, algebraic, and blah. So when I'm saying basic here, I mean basic as compared to all of that. We're going to do some non-trivial stuff. I mean, some of the stuff we're going to do is actually pretty cool. But this is still basic. Why are we going to do that? Our goal, okay, if you want to see a motivation for this, is one thing from cryptography is to understand in detail one specific protocol, to understand in detail the RSA public key cryptography protocol, okay, which is based essentially on number theoretic principles and one complexity theoretic hypothesis. I'll get back to that, okay? So the cryptography part, I will do in a couple of weeks separately, once we've built up all the number theory we need to do the protocol, okay? That's okay. So there is one ingredient which will be missing, which is induction. What is induction? It is a fundamental axiom of the integers or the natural numbers. We will see this in chapter 5. I agree with the book this time that doing induction first is not good because it's still very technical, but it would be more logical to do it now because I mean, every half hour I'll be saying, I can't prove this because I need induction. We don't have it. Okay. So you'll just have to believe that there is a way of proving these things and it's induction. But it's sort of semi-technical, so we are just going to keep it for later. So for pedagogical reasons, it's more fun to do the number theory and cryptography now and induction after. Okay, so that's the reason, but it's not logical. So we'll see that later. Okay, all right. So let's start. 4.1, section 4.1 is divisibility in modular arithmetic. So unless otherwise specified, everything here deals with integers. So when I'm saying there exists something, or for all, unless I specify it, it's going to be everything is integers here. We are living in the world of integers. So unless otherwise, so sometimes I'll mention fractions, but rationals, unless otherwise specified, all numbers involved are integers. Okay. All right. So our first definition, very basic definition. And you might remember from a couple of weeks ago or a week ago, I said, please, when you're working with integers, don't divide, don't use fractions. And here it's going to be very tempting to do this. Never do it. Don't do it. Slap on the wrist. Okay. Okay. So here is our first definition. I have two integers. I'm mentioning they are. Then we say that A divides B if there exists, and I'll be using the quantifiers to go a little faster. If there exists some C integer such that B equals to A times C. Okay, so another way of saying this is that A is a divisor of B. A is a factor of B. You will also see this, or B is a multiple of A, right? I mean, you know what this is. You've seen this before. Now, I will write this once, but again, you should try to avoid going to the rationals when doing arguments. And I mean, I'm telling you, it's just, if you're going that direction, it's almost for sure going to go wrong. Okay. But I will still say this just to be sure that we all understand. Oh yeah, I should, do what I want. Okay. Notation. Be careful, it's not a fraction. A divides B. This is a vertical line. Okay, so that's a notation to say that A divides B. Fact is that A divides B if and only if the fraction B divided by A is an integer, right? But please try to avoid fractions in arguments, proofs. It's not the right way. It's really not the right way to do this. Okay, I'm telling you. Just okay. All right. Here are some examples. Then it's silly, but let's do them. 2 divides 6, right? 4 divides 100. Why? Because 100 is 4 times 25. 3 does not divide 98, right? That's what I mean, okay? So 98 is not a multiple of 3. Okay, you know what I'm talking about. Let's do a little theorem. So in the book, they call it a theorem. Actually, this should not be, I mean, this should be just a little lemma, but I'm going to use the same terminology as the book. So if you're reading the book, you're looking at the book, we're talking about the same thing. So our first theorem, if I have 3 integers, A, B, and C, A is not 0, then the following are true. 1, if A divides B and A divides C, then A divides B plus C. That's our first statement. Second statement. These are very useful little things that we're going to use all the time from now on, okay? If A divides B, then A divides B times C for any C. Okay, I'll just write them out and then I'll discuss them and then I'll prove them. Maybe not all of them, but and then transitivity of divisibility. If A divides B and B divides C, then A divides C. Okay, so let's just illustrate this. Oh yeah, by the way, I didn't see that much and I'm very, very happy. I didn't see that. I didn't ask enough questions to see it, but if you're proving a statement, this is obvious, but if you're proving a statement that says for all blah, 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 then don't say, for example, if don't even write it. You can do it on scrap paper, not show it to anybody, that's fine, but don't write it. It's just like everybody is an idiot, proof Donald Trump. That doesn't work, right? It's not a proof, right? I'm sorry if you don't think Donald Trump is, if you don't think he's an idiot, I'm sorry. Maybe he's not, I don't know. It was a joke. I apologize. I'm sorry. I don't want to lose my job. No, I'm not drunk. This is tea. Nice sunny day outside. I'm recording this. I shouldn't be doing this way. I'm sorry. Okay. Yes. I'll be fine. Yes, I hope so. I don't know. I'm not sure anymore. Okay, so let's discuss this just to illustrate, but these are not proofs. So what does the first one mean? It means that if a number divides two numbers, then it divides their sum. I hope that makes sense. I will prove it, but I'm going to give you an example, but this is not a proof, right? It's just to illustrate what this means, right? If B is a multiple of, so if you have two multiples of 3, then their sum is a multiple of 3, right? So the sum of two multiples of, let's say, 3 is also a multiple of 3. Okay, so this is what I'm saying here. This is to illustrate what this says. Okay, second one. If A divides B, then A divides any multiple of B. So yeah, so if B is a multiple of 3, then any multiple of B is a multiple of 3, right? So if B is a multiple of 3, so is any multiple of B. It's still divisible by 3, right? And the third one is the transitivity, right? A divides B, B. So if C is a multiple of B and B is a multiple of A, then C is a multiple of A. I hope that makes sense, right? So you see what I'm talking about. Now, I'm going to prove the first one, and the next two are exercises in the book, right? So these are exercises in the book, assigned from the book. So you should try them. I'm going to prove the first one. Okay, so now this should work. No, don't do that. Here, like that. Yeah. Okay, here's the proof. Okay, so this is just a straightforward proof. So if A divides B means, so I'm just applying the definition, it means that B is a multiple of A, means there exists some C integer, I'm not writing it, everything is an integer here, such that B equals to A, oh, not C, bad choice. You see where I'm going with this, that's bad. I don't want to use C because it's already in the, let's call it U. There exists a U such B equals AU. A divides C means there exists a V such that C equals to AV, right? I'm just applying the definition. So now I want to show that B plus C is a multiple of A. So I'm just going to add those together. B plus C is AU plus AV, which is A times U plus V. So we're done. Right? That's it. Hopefully you see it. Okay. The other two, I'll leave them as exercises. You should try them. It's just following the definitions. Okay. So hopefully that's good. Here's a little corollary, which is like super useful and somehow it gets forgotten. I don't know. Here's a corollary. Again, that means it just follows from what I just did. So if I have 3 integers, a is not 0, satisfy the following. A divides B and A divides C, then A divides M times B plus N times C for any Mn integers. Okay, let's try to parse that. So I've been a student and I've been a student of math. So I remember sitting down in a classroom and the professor writes a statement like that and you go like, okay, haven't parsed it. It's just a bunch of symbols. I don't see it, okay? So let's go through it again. So I'm saying that if a number A, all integers, divides B and divides C, then it divides any combination of these two by any multiple. So you multiply those two numbers, B and C, by whatever you want, integers, you add those together, and you still have a multiple of A, okay? If this is obvious to you, obvious in the sense, be careful, but if you just, yeah, I believe it, it must be true, that's great. If you don't believe it, that's also great, because then you prove it, and then you know it's true. So let's prove it. I am going to use everything I built in the last theorem, okay? So A divides B and A divides C, and I want to show that A divides MB plus NC. So let's start by using, let's go back over here, sorry. Let's go back to number 2. It says that if a number divides another number, it divides any multiple of it, okay? So I'm gonna be using that, right? So by theorem 1, A divides B implies A divides MB for any M. By the same result, A divides C, that means that A divides NC for any N. So if you divide a number, you divide any multiple of it. And now I want to show that it divides the sum. We just proved that. That was the first. So by theorem 1, first statement, that means that A divides the sum. So it divides the two numbers, so it divides their sum. Okay. What time is it? Man. Okay. Yeah, sort of irrelevant, but you might see this. Some old geezers use this. This was used many thousands of years ago. Many hundred years ago. It means what had to be proved. Quod erat demonstrandum. It's Latin. It means what had to be proved. So that was used quite a bit, a long time ago. Now we use a little square. I had a stats professor in university who would write LEK at the end of every proof. It took us a long time to figure out what he meant by this, but we figured out it meant l'affaire ketchup. So that was his little gag, but I'm not going to be using that. Okay, but okay, he was a funny guy. Even though he taught statistics, which was the most boring course I ever took. But anyway, sorry for those who like statistics. It was just a boring course. Okay, next up and last.
Quick question.
Yep.
Concerning theorem 2 part II.
Mm-hmm.
If A is, let's say A is 4 and B is 2, that would be correct. But if, for instance,
no, it's the other way around, right? A divides B.
Yeah, but
So
if sorry,
says the small A would be 2 and B would be 4, right?
Right.
Or I don't know, maybe what are, okay, sorry, forget that I said anything. Just keep on going. Just go ahead.
Okay, no, I just figured it out.
Yeah, okay.
That's all.
All right. Okay. So then, all right. So our next theorem is like a biggie. I mean, it's like molto importante. Really, really, it's a big one. Okay. And it's theorem 2 in section 4.1. It has a funny name. The name of this theorem is the division algorithm, which is a funny name because it's not an algorithm. So it's the so-called division algorithm, but that's its name. I mean, there's a reason why it's called like that, but it's like in statistics, random variables, which are not variables and not random. One of the many reasons I don't like statistics, but anyway. So, but they're really important. It's not my cup of tea, that's all. Okay, so here we go. Here's the statement of the division algorithm. This is like super important, and we're going to be using that all the time. So let me write it, and then we'll analyze what it's supposed to mean, and I will try to convince you that it is true. I think I can prove it without induction, but anyway. So here's the statement. If you take any integer a, and you take any other integer d, but d is positive, I'll write it in words here, then there exist unique, and this is like super important, q and r integers with r greater or equal to 0 but strictly less than d, such that, I know it's awful, eh? Already you're going like, what the hell's going on? Such that a equals to qd plus r. And now you're thinking, man, if we're going to use this all the time, what am I doing here? Okay, it's not as bad as it feels right now. Okay, so what is this saying? Okay, what is this saying? Let me just I'm going to illustrate it, and then I'm going to try to make you understand what this is about. And there's a good chance you're going to believe this even before I prove it. Okay. The names, the letters have been chosen specifically. So D for divisor or divided by, but Q for quotient, R for remainder. So what you're looking at here is A divided by D, right? But these are all integers. So we're dividing A by D. So it's Q times D, but there's a remainder, right? Because maybe D does not divide A. A is maybe not a multiple of D, right? So there's a remainder when you're dividing. Hence the name division algorithm. It's like dividing A by D, okay? But it's a theorem that says these numbers exist, which is sort of important, but it's the fact that they are unique, which is like super useful. That's the really important part here. Okay. I mean, both are important, but uniqueness, if you forget uniqueness, you'll be in trouble. Okay, so here's an example just to illustrate what this is about. If you take A equals to 50 and D equals to 4. So I want to write 50 as a multiple of 4 plus some remainder. Now notice the remainder has to be, I mean, if you remove the condition which is here, then this is a silly statement. It won't be true for the uniqueness, but that's the key, right? You want that remainder to be between 0 and what you're dividing with, okay? So this is really crucial. Okay, so here, what is it? Well, you take 50 and you look at how many 4s you can put into 50, right? If you put 12 of them, you're going to reach 48. And then if you try to put another one, you're going to go over, right? So this is 12, I'll write it, yeah, 12 times 4, 48 plus 2. So this is the Q, and this is the R, and it is between 0 and 4, right? Okay, so this is an illustration of what this is doing. So you're dividing 50 by 4. You take as many 4s as you can fit into 50 without going over, and you'll get a remainder which is between 0 and strictly below the what you're dividing by, right? Because if you had another D, you would add it to Q, right? You could fit another D in your number. Okay. Okay, so why is this true? I'm going to, which is basically what I've been miming like this and explaining is sort of my proof. Okay, so here's my proof of the division algorithm. Okay, so consider the largest integer Q such that Q times D is less or equal to A, which is exactly what I've been saying, right? So you count how many D's you can put into A. You try to put as many as you can, right? So that you can maybe put Q of them in there, okay? So notice the following. So if Q is the largest possible integer such that Q times D is less or equal to A, what can you say about the next guy, Q plus 1 times D? So in our example, let me just do a little example. I had A equals to 50 and I had D equals to 4. I want to put as many 4s in 50 as I can. I can put 12 of them, right? 12 times 4 is less or equal to 50. But if I try 13, I go over, right? So this is, I do exactly the same. Bart Simpson. This is strictly less than 13 times 4. Agreed?
Yes.
Yes, I got a yes. Yes. Right. Okay. So if Q is the largest possible number of D's that I can fit into A, it means that Q plus 1 times D must be bigger than A, right? So QD less or equal to A, strictly less than the next one, right? If I try to fit another D, I'm gonna go over, right? Because it's the largest. Okay. All right. So what can I say? So now A has to be greater or equal to QD, but strictly less than Q plus 1D. So it means it must be here. So maybe it's QD, maybe it's QD plus 1, maybe it's QD plus 2, blah, 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 blah. But the biggest one it can be is QD plus D minus 1. That's the biggest it can be, right? Because the next one, these are all integers. The next one would be QD plus D, but that's Q plus 1 times D is too big. Everybody is okay with this up to this point. If I try to fit another D, I'm going to go over. Yes. Yes. Okay.
That was a sex joke. My bad.
Okay. I sort of guess it would be. Okay, I'll erase it. Yes. I just don't want to understand it. That's good. Thank you for being so honest. That's wonderful. Yeah, I lost my train of thought. Yes. So numbers, integers, math. Yeah, so A is one of these numbers, right? So in other words, so A is equal to QD plus some number between 0 and D minus 1. Which is exactly what we wanted, right? That's the proof of existence. So this proves existence. Okay. Now I want to show uniqueness. Yeah. I'll have to cut that out. Yes, bleep. Actually, no, the chat is not recorded, right? Oh, I forgot to do something. You're all going to be live on YouTube. Almost. No. Okay, now it's better. Make that bigger. I think that works. Okay, the chat is not on YouTube, which doesn't mean you should put everything that goes through your mind on it. Okay, we've got existence. I feel so alone. Uniqueness now. Yes, uniqueness. I'm sorry to keep you waiting. Uniqueness. How do I prove uniqueness? How do you prove that they are the only ones? So what you're going to do is to suppose that there's another one and show it's actually the same. So here's how you prove this. Suppose that A is expressed in two different ways. So A would be QD plus R, right? Maybe the ones that we just found. And maybe it is another one also, Q prime D plus R prime, where R and R prime are greater or equal to 0 and less than D. What do I want to show? I want to show that Q equals to Q prime and R equals to R prime. Okay, this one is a little... Okay, let's do it. You're grown-ups, we can do it. Okay, so how do I do that? Well, I've got QD plus R equals Q prime D plus R prime. I'm going to put all of one stuff on one side and the other stuff on the other side. That's very mathematical. QD minus Q prime D is equal to R prime minus R. Everybody's good with that, I know. Yes. And so Q minus Q prime times D equals to R prime minus R. Right? But now here's the killer argument. R and R prime are little baby numbers between 0 and D. So if I subtract them, it shouldn't get really big. Of course, you say, wait, maybe it's a negative. But if I take them in absolute value, right, these numbers are close to one another, right? They can't be very big, very, very far apart. But this equality says it should be a multiple of D. So that's very unlikely. So notice, right? So R and R prime are between 0 and D. So we know this, right? So if you look at their difference in absolute value, right? This must be less than D. They can't be further than D apart. It's not possible. Do you believe this? So 0, 1, 2, right up to D minus 1. So R and R prime are here. By absolute value, just take the bigger of the two minus the smaller of the two. Can this be greater or equal to D? No, obviously not. Hopefully you believe this. Yes?
Yes.
Yes, excellent. All right, but look, so I have that this number is a multiple of D, but it's smaller than D and greater or equal to 0. I'm sorry, I'm going, so r minus r prime is a multiple, sorry, it should be the other way around, but it doesn't matter, right? Is a multiple of D, but is smaller than D. Consequence, it must be 0. There's no other possibility. Right, every number divides 0 because D times 0 is 0, right? So 0 is a multiple of D. That's sort of stupid, but that's true. Okay, so this number is too small to be 1 times D or 2 times D or 3 times D, so it has to be 0 times D, okay? So if R is equal to R prime, I conclude that Q equals to Q prime and I have uniqueness. And I know I've lost some of you, right? So R equals R prime, Q equals Q prime. So we have uniqueness.
Can you go up just a bit?
Yep. Sorry. Yes, here.
Yeah, I just the bottom of the page.
Okay, I'm hiding the chat. I just can't. I can just, no.
Okay, I'm okay now.
All right. Yes. Okay, what time is it? It's 1:30. And I will stop here. I don't want to do any more now. That's enough. Yes. Naughty, naughty kids. Okay, any questions, comments, jokes, clean jokes? Some of you had questions for me. I will stop the recording here. Stop recording.